invite. Cool, right. I'm going to share my screen and try and share some slides. Right. Okay, can you see that, Michael? Is everything coming through?
I can see that.
Excellent, cool. Okay, so well, thanks for the really kind introduction, and thanks for the invite to speak here. It's always great to talk to people interested in planning, and I think planning is such an exciting field that's got so much to offer, and I expect it to be doing more in the future, which is great. So I'm going to talk, as Michael said. I mean, Michael also alluded to the fact that I do a lot of different things. My PhD was in planning. My main interest is in decision making for autonomous systems, particularly mission planning. So deciding how to achieve a particular task or a goal for a robot or an autonomous system. And the sort of pitch of the talk is around long-term autonomy, which is the ability for an autonomous system to act robustly, reliably, intelligently for long periods of time. What that means, what we treat as long, really varies, and it depends on the application and the environment. We've seen Mars rovers running for years autonomously, but often in labs in more challenging settings, we can't get past hours of autonomy for particular tasks. So the notion of long is a kind of movable feast. You can use sort of define it as you will, but in general, we're going to think about some kind of extended time horizon, maybe multiple days. That's where things get interesting, I think. But we'll come to that a little bit more in a minute. What I want to do before I get started is to thank all my co-authors. So this is a subset of all my co-authors, but these are the people that have contributed to the work that I'm going to talk about today. I'd also like to acknowledge all the funding sources that have led to this. So I couldn't have done any of this work without these wonderful people. And that's always true. A lot of what we do, particularly when you think about more complex systems, robots, etc., requires a team effort. And I think a lot of excellent science requires team effort. You need to bounce your ideas off people. You need people with different skills. And particularly this kind of area where we're thinking about deploying software on real bits of machinery that needs formal guarantees or extensive testing. You need people with expertise from formal computer science all the way down to kind of systems engineering. So a broad range of expertise are necessary for this kind of job, and you can't do it without teams. So a huge thanks to the people, the other people that have contributed to this work. Of course, as the kind of standard disclaimer goes, I will butcher all their great ideas. So they've all got the kind of key ideas. I'm going to give you a jumbled and personal retelling of the stories that are in their papers and are in their work. So I also ask for their forgiveness for what I'm about to describe. Speaking of collaborations, I'd also just like to flag up, well, first of all, describe or follow on what Michael said. So in Oxford, I lead a group called the Goal-Oriented Autonomous Long-Lived Systems Group, or GOALS. And we're part of a wider institute called the Oxford Robotics Institute that has about seven or eight kind of parallel groups of similar size, all working on different areas of autonomy for robotics, everything from kind of localization and control up to semantic and cognitive understanding. So we're part of a wider infrastructure, all pursuing the same aim of kind of creating and fielding robust autonomous systems. And the reason I wanted to talk about this is, one, is it's going to lead into the rest of the talk, because I'm going to start describing what we mean, at least by goal-oriented autonomy. And also to flag up the thing that you can see up in the top left of your screen. I'm trying to invert the image, that I'm currently looking for a postdoc. So we've got some new funding to grow our team, and we're looking for a postdoc to join us. So that role will be on planning of whatever sort you're interested in. It's a very broad position, but please get in touch if you're interested. If you're coming towards the end of your current contract or you're finishing up your PhD, please give me a shout, because we're looking for excellent people, ideally with some kind of experience of planning. Okay, so also I should say, I'm going to repeat because maybe it helps coming from me. I'm really happy to take questions as we go. Just stick your hand up using the hand up functionality in Zoom, or type into the chat that you want to stick your hand up, and then we can interrupt and take questions. It's usually much better if people interrupt and we deal with the questions as we go. If it gets a little bit out of hand, if we're talking too long on kind of some small point and I'd rather move on, then I can manage that. That's up to me. Okay, so the first bit will be a bit of a recap, I think, of things you've seen throughout the week. So my research group and my research interests in general are around systems, agents, robots that are goal-oriented and autonomous. So this is because we want our robots to be useful, right? They should act to achieve things in their environment. That might be completing tasks, goals, or missions, right? These are all roughly synonyms. They tend to be used slightly differently in the community, but often they describe what we want our system to do. And for some applications or with some end users, they prefer to specify the whole task without some details. In other cases, you want to describe your goals. Ultimately, these lead to missions, so extended periods of autonomous behavior to do something useful in the environment. The field of planning, so this is a slide I use for other talks as well. You know now that typically what we have to do to achieve this behavior is come up with some sequence of actions that achieve that purpose. But often that sequence of action will come under some set of constraints. And those constraints might be explicit or implicit in the task you're doing, and they may be on the goals, on the actions, on the resources. And I'll talk about constraints a little bit, but what you find in robotics in particular is there are always constraints. You may not always choose to model them in your planning domain, but the idea of constraints is always key. This is because a robot is typically limited in its capacity for action in terms of power. It might be limited in its ability to be safe and robust in particular environments, or it may be deployed for a particular period of time, for example, a time duration for its mission. So constraints on the plans and on the processes are something that are interesting. And in general, this not just interested in individual tasks or goals, we're interested in what we call missions, and those missions might last from minutes to months. So a mission is deploying a robot into an environment to achieve a particular goal. And that goal could be a recurring task, like to ensure that every fence in a facility is inspected twice a day, or it could be a very kind of targeted mission of retrieving an object from a disaster zone, for example. So there are many different types of missions, but we think of a mission as the thing you're putting a robot into an environment for. And that may have, yes, a sequence of tasks, a single task, a repeated specification, or many things like that. So I'm going to be purposely vague because this encompasses everything you've heard about so far, I think, this week. So again, hopefully this is just a huge amount of revision. There are a bunch of ingredients into a mission planning system. And the reason I'm setting these out is because I want to use this to focus on the areas that I think are important for this talk. Not that these other areas aren't important, but there's a sort of subset of the areas of planning that I find are particularly interesting for the work we do. So as you know, you have some kind of model that describes the world, that captures the sort of domain, or almost the domain physics is one way that people describe it. You've got some specification, and I'll use the term specification typically when I'm talking about the goal that you're trying to achieve. But we generally think of a richer specification language, which is both the goal and maybe some objective function, some set of constraints, etc. So the specification describes both what the robot is trying to achieve, what the system is trying to achieve, and the constraints or preferences of the user. We then chuck all of those things into a planning algorithm. The output of that planning algorithm would be a plan, but there we might think of that more generally. It might be a policy, a controller, a state machine, a behavior tree, a timeline. All of these things are kind of outputs here. In particular, we're going to focus on policies because we're going to do a lot of planning under uncertainty in this talk, and policies are required there. But in general, you can get all sorts of things out of these algorithms. And then we feed it onto robot execution. So a lot of what I'm going to talk about today is going to be processes that generate policies that are run on robots in the real world. I'm not going to talk about execution. There's excellent work, and you've already had amazing talks about the problems of executing actions and policies and plans on robots. So, you know, a lot of your speakers have done, there's a lot of interesting work happening in that area at the moment, but we're not going to focus on that for here. So the bit that's worth zooming in on, I think, is the model. So planning is a model-based discipline. Every variation of planning you've seen assumes some model of the world existing in order to reason about. And this is where things get interesting in robotics, I think. So if you look at the history of AI methods applied to robots, planning and model-based AI often comes in for criticism because it's viewed as brittle. So it's brittle because we make these models, these precise, elegant models in software and in maths, and then there's a mismatch between the model that's in the robot's head or in the agent's head and the way the world actually behaves. Okay, when we make a model, we perform some abstraction. That abstraction necessarily throws away the detail, and our model-based approaches can be very prone to error because of that missing detail. Or if not prone to error, then requiring a stack or a set of layers of kind of interpretations between the model and the execution. And that sometimes kind of washes away the benefits of some of the model-based approaches. So this is a kind of historical criticism, but there's you can't get away from models. So if you're thinking about reasoning over long time horizons, in fact, typically beyond a single action or a small number of actions, you need those models. The computational complexity of search and of building lookup tables and policies is such that if you don't have a model to structure your reasoning, then you're really not able to do this kind of long-term behavior. So for me, models are essential, which means we have to overcome the problems of mismatch or brittleness, right? We have to make our models more like the world's. And so that leads to the general approach that my group takes, which is we create models from sort of two sources, right? We create models from fixed structures, which are the kind of more classic models that you might see. Those fixed structures encode the set of assumptions about the world or the physics about the world at a high level. And those are essential to provide the ability to search over large spaces. But what we'll demonstrate in this talk is that what we really want to do is then parameterize or fit these models to data that we gather from the deployment environments using machine learning approaches or other statistical approaches. So for us, the solution to this kind of conundrum of needing models but then being brittle is to inject into those models data that we've got from robot experiences in the real environment. And I would argue that that is key to being able to build autonomous systems that are robust in their behavior in the real world. They need to use data from that real world to build models that they plan their behaviors with. I'm not going to present any evidence that this is the right way of doing it. This is kind of a hand-wavy philosophy. This is what I think is the right way of doing things. But typically, this is a broader question that we can discuss at some point. So that's going to be my general pitch for the talk. I'm going to demonstrate a number of ways that we take models that have some fixed elements or some assumptions, show how we can put data into those models from experience and from learning. And what that then leads to is a whole bunch of new challenges in terms of creating planning algorithms and autonomous systems. So whilst this to me looks like a solution, the solution raises a whole number of questions about how we can plan and reason with these kinds of models, or what the best way of doing it is.
Nick, quick question. Why do you emphasize the fixed structure of the models? Why does it have to be fixed?
Well, so ultimately, you're writing down some assumptions that might be which states are available to transition to other states, right? So there's some structure in a model that comes a priori. And that's all I'm saying here. By fixed, I really mean before you put the data in. So of course they are dynamic in that they can describe dynamic scenes or the dynamic environments or time varying properties, but I mean fixed as in there is some scaffolding that you provide for that to happen with. So I don't mean that they're only dealing with static or deterministic worlds. In fact, I'm specifically not going to talk about that. We're doing the opposite, but I mean that there is some scaffolding to provide some structure.
Makes sense. Thank you.
It's okay. Great question. So yeah, please, those kind of questions are ideal. I will say that this idea, in fact, I'm going to jump to the next slide because I think it kind of captures the way I'm thinking at the moment. So this talk is going to be a kind of what I decided to call a sort of scruffy overview of the work my group's been doing to merge these general ideas. So we're going to focus on the sort of left-hand side of this set of ingredients. So we're going to look at models, specification languages, and planning algorithms. And in particular, we're going to look at Markov decision processes. So you've already had a lecture on planning under uncertainty. And so we're going to leverage that to sort of talk about ways that we can apply MDP planning with ingredients that come from learning for robot applications. but I see this as a sort of scruffy, kind of slightly hand-wavy overview, because we're still developing what I would see as a kind of underpinning theory that brings all this stuff together. This to me feels like a really good idea, and an idea whose time has kind of come, I think. But I would say that we don't have a formal theory or a formal way of putting all this together yet. So these are examples drawn from experience of building and deploying autonomous systems that motivate the need to approach the problem like this. But yeah, this is me still trying to synthesize actually the kind of the next stage of the vision for my group. So I'm kind of actively doing that while presenting talks. Okay, so that's the general idea. And the way that the talk is going to be structured is that I'm going to start by giving you a kind of general overview of the approach that we carried out for probably our most high profile piece of work that sort of got us started on this route. And that will give you an idea of both kind of an example of a long-term autonomous system and a specific model specification and algorithm that we use to produce long-term autonomous goal-driven behavior. And then in whatever time is left, I'm going to then show you some examples of kind of the consequences or the extensions of that work. So where we went next with these kind of models. So the first bit is going to be maybe a more focused talk on a particular approach we took. And then later on, I'm going to give you some examples of other ways that we can use that methodology to achieve interesting robotic behavior. Of course, anytime, ask questions and we can go from there. Cool. So the first example, or the motivating example, came from a project called Strands. It was a European project that ran for 4 years, from 2013 onwards. It involved partners from across Europe. And within this project, we were focused on deploying autonomous robots in everyday environments. So very much dynamic, flexible, uncertain environments. Within the project, our aim, which we achieved, was to have these robots deployed unsupervised, so no computer scientists, no engineers on site, with autonomous behavior, doing useful tasks in that environment. So these robots had to respond to requests for tasks to be performed by humans in their environment. They had to manage their own battery life. They had to act robustly in the dynamics of real workplaces. So offices on the left and the right of the screen, a hospital in the middle of the screen. And we were deploying these robots to, alongside people's real jobs. So we had to manage a huge amount of different things in these elements. But the idea that the robots would be in this environment and all that variation I've talked about requires planning. So it's a great use case for the kind of technologies you've been looking at this week, because without it, you couldn't pre-script. You absolutely cannot pre-script or pre-specify how the robot should behave in these environments at a fine-grained level, because the environment is different every day, every hour. The set of tasks is different. The resources, the robot's battery changes at different rates. The world gets reconfigured around the robot. So if you don't have onboard online decision-making, you can't have autonomous behavior. So for me, this is a real kind of key motivating use case for the kind of work we're talking about. And so this was our aim. And what you see here is kind of the end product, the robots kind of driving around doing stuff. I should say, and you'll get the PDFs of these slides, you can see the videos. On a bunch of the slides, there'll be some citations for further reading. I'm also happy to take specific questions on those papers and things as we go. Okay, so this is the motivation. The first thing we can think about when we're deploying a robot into this environment is, what is the model? How are we going to describe the robot's task environment? Well, a mobile robot typically operates in a 2D or 2.5D continuous world. So it works on a map. So our robot is mobile. It's performing tasks around an environment. So you start with a spatial representation, typically a continuous spatial representation, such as a map like this. But for decision-making in any scale, you typically need some kind of discretization, some kind of abstraction. And this is where the modeling starts. This is where I start talking about this kind of fixed structure or scaffolding. And in particular, in this environment, we discretize the continuous spatial world into a graph. So we refer to this as a topological map. It's a directed graph. The circles are nodes, which describe areas the robot can stop and do something, or key locations the robot must pass through. And the edges in the graph describe the connectivity of the spatial area So the robot can move from one node to another node without entering a third node. That's the approximate semantics. The edges are directed, and the edges are actually labeled with actions the agent can perform. So this graph-like representation already should be kind of conjuring up some kind of transition system in your head, and that's exactly what we'll end up doing. So the nice thing about having a topological map like this is it gives you a way of labeling the environment in already a kind of declarative way about what actions are available to an agent. In particular, for a mobile robot such as this, we worked on labeling the edges with different navigation actions. And this concept of kind of different navigation behaviors is something we'll come back to throughout the talk. So for example, the robot in free space would just navigate using a kind of continuous motion planner. If the robot had to pass through a doorway, as you see here, the robot needed a special behavior to wait for a nice friendly human to open the door and hold it. And to charge its battery, the robot had to autonomously dock onto a charging station, which you can see that's down here. We can also describe the actions available to the robot at certain locations. So at certain locations, the robot was able to, for example, search for objects or observe humans in order to learn about the activities they're performing. So we're building a domain description here of the structure of the environment and the actions that are available to it. This, again, should be familiar from the kind of planning work you've seen throughout the week. Where things become interesting in terms of long-term autonomy and in terms of robotic autonomy is that this world is not deterministic. So what we see when the robot tries to navigate or try and move between two locations, two nodes on the map, it's prone to failures. So there's all sorts of things I could say about these failures. And all sorts of things I could say about the dynamics. I've got a whole other talks about this. But the key thing to think about, well, there's two aspects that we can focus on. One is that in general, the robot can move between two locations in the environment successfully, but at certain times of day, under certain conditions, the robot fails to navigate. So for example, on the left up here, we can see the robot's got stuck on a wheeled chair. So it has a very sensitive bumper around the bottom here. Can you see my mouse? Just to check.
Yep, I can see it.
Cool. Okay, so around the bottom here, you can see the robot is touching a chair, and that chair triggers the bumper, so the robot can't move. This is the robot's charging station, and a cleaner, I think fairly adversarially, positioned a brush over the charging station at the time of day when the robot normally charges. So the robot here could run out of battery, and in a long-term autonomy setting, running out of battery is the absolute thing we're trying to avoid. One of the reasons we try to avoid it is because, as I said, the aim for this was to not have engineers or computer scientists on site, and the deployment sites were typically half an hour, 2 hours away from where we all lived. So one of us would have to drive there and fix the robot, which none of us wanted to do. So failures occur. They occur with some probability in this environment. The other thing is time. So in this case, we often, and actually in many service robotic tasks, you care about the duration of actions and you care about bounding the robot's behavior to time. Perhaps there's only a certain amount of time when the robot's allowed to be on the floor of the office. Often, and we did this in practice, the robot's tasks were tied to particular times. For example, you had to meet a VIP at reception at 9 AM. Therefore, the robot needs... Oh, yes.
Louisa's asking, why is it a directed graph?
Because ultimately, so it's a directed graph because bits of the environment, the robot may only be able to pass in particular directions or only successfully pass in particular directions, because the localization and navigation does perform differently going one way through a corridor to another. So the kind of real physical behavior of the robot can vary when passing in different directions between nodes. In practice, we largely kept the graph as, even though it's directed, most nodes had a pair of directed edges between them. So the robot typically, the construction of the map was typically fully connected. Sorry, not fully connected. Each pair was connected in both directions. So the addition of directed edges gives us modeling power, particularly when deploying a robot in the environment, but we didn't always use that. The other way to think about it is a good example of where we used it was on a ramp. So at the University of Lincoln, they had 2 levels of their computer science department separated by quite a steep ramp. And depending on whether you're going up or down the ramp, you needed to change the force the robot was applying to its motors. And so we had kind of a node at the top of the ramp, node at the bottom, edges between them, and the actions on the edges were different because they included different parameterizations for the force on the motors.
Thank you.
Cool. And so these are all great questions because they're really about what happens when you take planning approaches, put them on robots and put them in the real world. Lots of things that maybe seem redundant from a pure theoretical perspective become important because they give you the power to influence. So a lot of what we did ended up being about having the power to alter the robot's behavior at a high level. So to be able to go in and change the actions available from a particular state is much easier than going and tweaking numbers in a config file for a particular location of the environment. So the more that you can propagate behavior choices up to a planning level, the richer, the easier it is to change that robot's behavior, I would argue. Happy to take more questions now if they're coming up. I see notifications popping.
Yep, I see one from Ben. Ben, do you want to unmute and ask the question?
Sure. Hi, Nick.
Hey.
I was wondering, so how did you first create the continuous map? Did you do that through autonomous exploration or from controlling the robot or from other means? And also, how did you then create the discrete map? You just said about there were ways that the robot behaved through some points differently. Did you have to try each connection and make sure there were no issues?
There's an element of that. So the first question, the 2D map was created using off-the-shelf tools in ROS. So every bit of robot movement you see is running in the robot operating system. And in fact, it's almost everything you'll see here is also open source in terms of these robots. So you can actually go down and download our tools, our planning systems, our task allocators, all of that is available to play with. So this is just a 2D map built from SLAM running standard nav stack. So we use G mapping and then we localizing it with AMCL. These environments are very big, hundreds of square meters. So it's a bit of a task to actually get them to create correctly. Then the discretization. So yeah, sorry, and to answer your question, we hand controlled the robot. So exploring in a human populated space of this size would just take forever and you'd have no guarantees on the quality. So since we were interested in behavior later on, we mapped these things manually and then we processed the map. I don't think this is the process version. We processed the map to remove dynamic obstacles. In fact, yes, it is. So let me jump back a few slides. If you look at this area up here where my mouse is waving, that is an open plan office area. So there's 20 chairs in this environment, well, maybe 30 chairs, random things knocking about. So we went through and we manually removed all the noise from the map. And so in general, you just see the static structures that the robot can localize against. In terms of the graph, we then apply that manually. And we typically, for this, we would have a couple of days of testing where we would set up the graph, we'd set up the map, and we'd have the robot just effectively randomly walking across the whole map. We gather statistics, and I'll talk about that a little later. And then we can inspect the statistics to look for failures, or we can just watch the robot. But yeah, there's a couple of days of sort of startup time of getting this stuff working well, because when you want to run for kind of months at a time, you really want to get all the annoying little bugs out, all the obvious stuff out to start with. So yeah, we effectively tested robot navigation across the whole environment. But in a fairly relaxed way. We didn't just run every edge a couple of times. We let the robot, because the other thing you find is that in these settings, the sequence of nodes you visit influences the behavior, because you come in at a different direction or a different speed or a different angle, depending on where you've been previously and depending on the dynamics of humans. So simply like repeating an edge won't give you necessarily a meaningful trial.
Okay, thank you.
It's great. Any other questions? I'm really, I mean, this is stuff I love talking about. So I'm happy to take more questions now if anyone else has other bits.
So Samuel Hall has a question. Would you like to unmute and ask it, or I can ask it as well?
Yeah, can do. Can you hear me?
Yep, loud and clear.
Perfect. Hi, Nick. Thank you for your talk. Could the robot deal autonomously with failures? So you had the charging point there on screen blocked by a mop. Could the robot decide to go, or could have the robot decide to go and find a second one? Or would it maybe have waited to see if the blockage is cleared, if it had enough battery life to last some length of time?
Great question. So I have another talk on this. There's a multi-level fallback system here. So within an individual action, you typically had a number of retries, single digits specified. So most actions, in fact, no, we took that out. So we had a policy executor that was allowed to retry actions. Within the navigation system, all navigation was embedded in something we called monitored navigation. So this was a state machine that you could specify for each action, which has parallels to the kind of various execution architectures I think you've heard about. For example, if you look at the Petronet plans kind of world, it was sort of similar in idea to that, but it was something we kind of engineered quickly to solve a problem. So it was able to retry under particular conditions. And in particular, general navigation failures, there was a sequence of fallback behaviors the robot would execute in terms of reversing, resetting its sensors, and then asking for human help in order to push it around safely in the environment. And we logged all of this data. So the robot could always come back, ask for help, and try and recover again. With the battery element, this was a really interesting open planning task. There are 2 charges in the environment, and the goal when the robot was sent to charge, it was given so all our specification was done in linear temporal logic, and I will talk about that a bit later on. The specification said, eventually reach one of your 2 charges. So the robot would try and reach one charger that gave it the best, I think the highest probability of successfully completing the task. If it failed, we actually had a problem because the model we're using was an MDP, and our MDP did not track the outcomes. Well, okay, you needed a special MDP to track the outcomes of actions. So what do you do on failure? In this case, your action fails, but you know your action fails with some probability anyway. We actually had the robot had no way of telling the difference between a failure due to kind of noise or dynamics versus what would be a permanent failure. I think it's a really open question for robotics, determining which types of failure you're experiencing. So we didn't really deal with that well. So in theory, the robot should be able to say, my goal says I can go to any of these 2 charging stations. In practice, a failure you would basically just keep retrying at that station until you timed out in some other. So we had probabilistic guarantees over our entire tasks. If we exceeded a particular threshold on the expected time of the task, we would then just terminate. But what you'd really want is the robot to say, I failed to reach this goal, this location, but I'll go somewhere else. But there are some subtleties that mean it's not quite as easy as it sounds.
Thanks.
I guess the other thing that's worth just adding to that is all of these things can be fixed. This was never a finished product. This was always a kind of a scientific testbed. And where we ended up working was really driven by the interest and the expertise of the team, and how serious some of the failures tended to be. So that kind of issue ultimately became a thing. We went, well, we know there's some interesting problems, but we haven't got time to do them. Okay, I'm going to move on, but I'm happy to take other questions later or in the chat or however you want to do this. Because actually the next, I've touched on it already. If we zoom into an individual edge, this is where we can start thinking about learning and statistics. So this is a histogram from a deployment of the durations of navigation actions on a single edge in the environment. We've categorized them already into successes and failures. And so this tracks, did the robot attempts to move on an edge? It can then record how long it took to complete that action. And it can flag that action as successful. So I went from A to B, or failure. I went from A, I didn't reach B. Maybe I reached C, maybe I got stuck. I mean, one of the things you see a lot in terms of robotic, or you used to see in terms of robotic planning under uncertainty papers, is people often say, well, localization means the robot is in one place when it thinks in the other. For indoor mobile robots, that almost never happens. Localization is very reliable. If you were doing underwater robotics, absolutely that can happen. For the kind of thing we're doing, the failures came from people, people or control in the environment typically. So we have a bunch of data points. And then what we want to do is generalize them. So we can take this data and apply effectively whatever your favorite statistical estimator or machine learning technique is. We did a number of different things in the project. Here it's simpler just to think about using something like a kernel density estimator to generalize from that data into a probability distribution. That now shows us a distribution over the time the robot expects to take for that action. We can see we have two different categories. So we have a probability distribution for successful actions. And that's a relatively, kind of as you would expect, it's a relatively clean single modal distribution. And the mean of that distribution is kind of roughly, how often is the main duration the robot takes. The failures get a lot more interesting. What you can see here is there appears to be two failure modes in the robot. Typically, there's a kind of fail earlier, and this is just for this edge, and it varies per edge. There's like an early fail. So the robot tries to act, and within 10 seconds, it realizes something's wrong. And there's a later fail where the robot knows that, the robot's probably been trying to recover and not done so well. You can actually also map these typically into the triggerings of this monitored navigation system. So the robot is going to try to do different things to recover. And if it recovers, it resets the action. So you can also consider that these are different recovery actions that are being triggered in sequence. And maybe the actions that were triggered here are successful. And if you get to here, it's because you've tried something, failed, and you're trying something else. So we're able to log this data and build probability distributions from it. We did something else, which is called Freeman, which does temporally based predictions, where we looked at how these things change over time. But that's a different talk entirely. The key thing to think about there is that the robot fails at different places at different times of day, and that is quite predictable if you know what's going on in the environment. And so you can exploit that in your models. Finally, what you can think about, one of the arguments for long-term autonomy, for repeating these missions day after day after day, is that you get better, or in general, you get better at predicting the performance of the robot on a particular edge. So this is one hand-picked because it's got a nice plot, but it shows it's part of the general trend. It shows how the robot is improving on predicting the mean of these distributions that we see. So the green is the mean of the success distribution, that as we go day by day or week by week, we get an improved performance in predicting that distribution. The red shows how good we are at predicting the failure distribution of the robot. And the black line actually shows how good we're getting, sorry, that's the failure duration. Black line is how good we are getting predicting the success and failure rate of the action in general. So the longer the robot moves in the environment, in general, the better its predictive power gets, the better its models get, the more it's adapted for that environment. So that is the kind of dream of this data and model-driven long-term autonomy. The machine learning, the statistics allow our system to get better at predicting its own behavior. The huge caveat in all of this is that the kind of environments we're talking about are non-stationary. So if someone moves a pot plant or a new person starts in the office, these distributions change. So whilst in general, for a stationary environment, you can get better at learning these models. In the more general case, the case of reality, these distributions are not stationary and become much harder to learn in practice. But we're able to, for a limited set of data, to show improvement in performance. Okay, so we've got some data. The next question is, how do we plan with that? Well, I mentioned at the beginning, we use a Markov decision process, and we'll use MDPs to underpin all the planning problems we'll see for the rest of this talk. You've had a tutorial on this, so I'm not going to go into the details. The key thing that distinguishes what we do is that we come again and think about this problem of some sort of fixed or automatically generated structure and some kind of learned parameterization. So in particular, for the task that we were looking at here, we have states and actions. and they are defined manually. In fact, they're defined automatically from the topological graph. Then we have transition probabilities and action costs, so the numeric, the continuous data, and those are the things we learn through experience. So the two sides of this slide really kind of capture the essence of what is motivating me for the work we're doing at the moment. We've got something that we know is kind of static and predictable, so the locations of the robots and how those locations are connected. And we've got other things that are a lot harder to write down in advance, things like the transition probabilities and the action costs, and those we learn from experience. So just to give you an idea, we take this topological map, we turn the nodes into states in our MDP, and then we can think about actions as being about transitioning between states. So this is a simplification of what we did in practice, but it gives you the rough idea. So we'd have an action of moving from node 1 to node 2, and through experience, we've learnt the probabilities of the transition probabilities. So in this case, you go from node 1 to node 2 successfully 85% of the time. 10% of the time you end up at node 3, typically because you're avoiding someone. So a human gets in your way, you navigate around them, you end up at a different node. And there's some 5% chance of failure. And actually, one of the interesting problems you have in applying these models is what do you do in failure? So failure, the robot isn't at node 1, node 2, or node 3. So one of the issues we have, and we keep revisiting it, is our spatial decomposition of the environment is non-exhaustive. So you can end up in bits of space that are not covered by any individual location in our map. Often the failures occur in those locations. So you have to think about how you recover from a failed state outside of your nodes. The other thing we're able to learn is the cost measure for these MDPs. So we typically do this in terms of seconds. So we could say that the cost of applying action A1 and ending up in N2 is 5 seconds, maybe 3 seconds for N3, and maybe 12 seconds for failure. But these are built from the predictive distributions we get from our statistics. So that's the general idea. Our states in practice are a lot more than just the locations of the environment. They typically track what the robot has been asked to do and how it's done it. So there's some more structured state into there. And I encourage you to look at the papers. We've got an IJRR article on this that covers the construction of the state in more detail. And the transition and cost functions we learn from experience. And that's something that we're going to talk about in some other contexts as well. What this means is we're able to generate a Markov decision process on the fly for a particular execution time. And that's one of the key areas for us for long-term autonomy, is that the model the robot ends up planning with is generated automatically given what it knows and what it's learned about the environment. So we call this a navigation MDP or a navigation and task MDP. So it's the model of the environment augmented with the probabilities and durations that we expect the robot to experience at the time of execution. So this isn't a general MDP for all time and all space. We only put in the transition probabilities that we expect for that time of day. So if you have some more interesting machine learning that can learn to predict for 2 o'clock on a Tuesday afternoon, then when you come to generate your MDP for 2 o'clock on a Tuesday afternoon, you'll have more specific probabilities and cost functions for that time of day. So that gives you an MDP that's adapted to the robot task environment and the execution time. So that's our model. Maybe just going to pause and ask slightly dangerously, has anyone got any questions?
So there was a couple of questions in the chat.
Okay.
One was from Shashank. Do you want to ask it yourself?
Yeah, sure. Am I audible?
Hey.
Yes. Yeah.
Oh, hey Nick, thanks for the talk. So I had a quick question. In the office example, you said so the robot needs a human to open the door to pass through the corridor.
Mm-hmm.
And how is that external dependency like accounted for or modeled when you plan for it? And since it also has a dependency on the battery and stuff.
Okay, so these are all amazing questions. So here we chose to fully abstract all of this. So the battery, and we'll talk about battery a bit later on, if there is a later on, but the battery is managed by a high-level task allocation system or task management system. The robot has 12 hours of battery life, and the robot's only acting if if the battery is above a certain threshold, effectively. So battery is always taken care of. What we tried to do in terms of our actions is we embedded some of these dependencies internally into the action. So the robot never had a dependency to first find a human, then try to open the door. Instead, that was just encoded into the action. So in fact, we didn't model the existence of humans in this action at all. The robot would just stand at the doorway and start shouting. So it would stand there, I mean, maybe not shouting. The robot would stop at the doorway and say, I am waiting to get through this door, please can you open it for me? And what would happen is that within a reasonable amount of time, a human would come and open the door because the human was going through the door anyway. So the robot would effectively wait for someone to arrive. So that's in some ways that sounds like you're ignoring a whole bunch of information. The interesting thing is, if you then learn the distribution of success transitions for that edge, you learn to predict at what times of day those doors are busy, and ultimately you only build plans that try and use doors when you're likely to be able to get through them. So the benefit of taking the methodology that we've done is that a lot of those details get abstracted into simple kind of probabilities and durations. So we no longer have to model individual humans. We just know that the success distribution of this action depends on the probabilities of humans being available. And we learn those implicitly by learning the transition and cost distributions for those edges.
Got it. Thanks.
Okay. I had a very simple question. When I saw the probability distributions over when the actions fail or when they succeed, so what are the durations of the actions, I thought, is it possible to use the ratio of the remaining probability masses as time passes as a kind of prediction whether or not this action is going to eventually succeed?
Yes, effectively. So what you want to try and do is you want to try and estimate which of these distributions you're in, and there are statistical tools to do that. We didn't do it, but you can effectively say that at some point for every action, if the duration has exceeded a particular point, you'll know which of those distributions you're in. It wouldn't work for all actions, but it does become predictable. And I think there's work from Maria Fox on turning this kind of data into hidden Markov models and using that to do failure detection. So I think there's some similar sort of work out there already,
Okay.
which is interesting, I think.
Thank
And
you.
ultimately, you want to do this because the sooner you can terminate a failing action, the more useful things you can do. So absolutely. We only did it at the high level. So we had a expected times to success of the whole policy, which we use to terminate policy executions rather than individual actions.
Yeah. So in the graph, the failed actions generally failed before the successful actions finished, but yeah. I know that there are many actions where that's the other way around, and you know that, okay, we're more likely to fail at this point.
Certainly for doors as well, right? So I think in general, if you've taken the time that's kind of one standard deviation outside your success mean, it's probably time to give up. I mean, that's quite an aggressive way of doing it, but that would be a reasonable way of detecting failure.
Well, you can tune the patience and pessimism of your robot.
Yeah.
Yeah. Okay. Mike has a question as well. Would you like to read it, or I can do that? Okay, I can read the question. He asks, what about humans changing their behavior in relation to the robot longer term? Was this taken into account?
So I think the answer there is the same to the question before Michael's. The answer is humans absolutely changed their behavior around the robot. They became more willing to help. They became less surprised. The way we thought about this and the way we think about this is that all of those factors effectively get compressed into the transition probabilities, the cost models, the things you're learning about the environment. And when I said earlier that the big problem is this is non-stationary, that's a great example of why it's non-stationary. If you learn the transition and cost probabilities from the first 2 weeks of the robot and try to apply them to the second 2 weeks of a deployment, there will be different behaviors from the humans, which means you'll get different, in reality, you'll observe different distributions in terms of performance. So, I mean, one quick and dirty way around this is just to learn from a windowed subset of your data. So you only learn from the last 2 or 3 weeks, and that goes to some way to describing this. Ultimately, you want to take into account recency effects, but that's getting a bit tricky. So yeah, they change their behavior. We don't explicitly take it into account. It makes the distributions you're learning, your target distributions, non-stationary. Effectively, they're non-stationary over a reasonable frequency, so you can sort of window your data and catch some of that.
Okay, thank you.
Okay, cool. I'm going to zoom on. I've loads to cover. I mean, I'm very much aware I'm not going to cover all of it, and these are absolutely what the questions I want to be asking, but let's cover it a little bit more. So we talked about the model. In terms of the specification, we used linear temporal logic. So we wanted to have a goal specification for the robot that captured temporal dependencies and gave us some flexibility. So I'm going to whiz through this because I think it's, given the questions I'm getting, I think there's other things I'd rather focus on. But if you haven't seen LTL before, or CoSafe LTL, so CoSafe LTL allows you to specify formulae that are evaluated over finite sequences of states. If you take away the CoSafe, then you're over infinite sequences. So this is a finite sequence of states where you can, as well as having the standard sort of Boolean operators, you can talk about the future. So you can say eventually, so sometimes in the future this should be true. You can talk about the next state, and you can talk about something being true until some other predicate is true. So this gives you a richer specification language, which is super important in the kind of service tasks we're doing. It allows us to do kind of what you'd think of as standard goals. So saying at some point in the future, I want you to have run a search for an object at this location. So that's what this bit indicates. It also allows you to structure your behavior a little bit more. So this is an interesting clause in the conjunction down here. This says, in the future, I want the thing in the bracket to be true. So I want you to have done this. And it says, I want you to be in this location, N3, and then in the next location, I want you to be in N2. That, in effect, forces our robot to travel a particular edge in the map at some point in the future. And we use that to gather data for bits of the map that were quite sparsely populated in terms of robot experience. So this was some way that we were able to have a richer set of experiences. LTL is now becoming incredibly popular in the robotics community. You'll see it in terms of, often it's called non-Markovian rewards in reinforcement learning, but it's used an awful lot in the verification and model checking community as a specification language for systems. And that's where quite a bit of our work came from within this project. The question then is, how do you use these kind of goals within planning or in MDP planning? And the answer is you create automata, so you can convert any LTL statement into an automata. So if you've got CoSafe LTL, this turns into a deterministic finite automata, like a nice simple structure. If you're using other forms of LTL, then you get things like non-deterministic Buki automata and things that get a bit richer. But this formula, I think there's not the time to go into the details here. This automata captures the progression of truth assignments in your formula. You start off in your initial state having not visited those two nodes. And in your goal state, you're guaranteed, if your automata reaches this accepting state on the far side, you're guaranteed to have satisfied the two conditions of your goal statement. This doesn't capture the transition over the state space of the robot. This is only the truth values of your goal statement, your specification. So this gives you a high level description of possible ways you can achieve your goal in terms of just finding out truth values. So the edges here are observations of predicates in your specification language. And to use this at planning time, we do something which is used quite heavily again in the verification of probabilistic systems community, and to some extent now in the planning and reinforcement learning communities. We take the cross product of the states in your MDP model. So on the left here, we have our simplified MDP. So in fact, it's a deterministic MDP at this point. And on the right, we have our automata. We then take a cross product to get a new state space. Then every state in our new state space includes one state, or a state from our MDP and a state from our automata. So down here, you can see that in our product MDP, we have one state which is being in N1 and having not observed the truth values of anything. There's another state which is I am in N1 and I've observed the truth values of N2 and N3. So I'm in this state in my automata. So this gives you a richer state space that tracks your progression through your goal. And you'll probably, some of you are getting a sense that not all of these states are necessary. Of course, there'll be some redundant states in this cross product, and good planning or solution techniques will prune those unused states out of your, unreachable states will get pruned later on in the planning process. What this gives is you can create a policy over this product state space, and the policy has memory now. So previously we're making a Markov assumption. We can't think about things that have happened in any other state than the one we're in. By including the automata from the LTL statement into our state, we're able to track what parts of that goal statement we've achieved previously. So that means for the same physical location or the same MDP location, we can generate different actions according to what we've achieved in our goal specification. So LTL gives you a rich language for specifying goals, and it allows you to leverage a whole bunch of kind of model checking and probabilistic verification tools as well. So in this work, we used LTL, and a few other bits of things I'm going to talk about. We use LTL as a goal specification language. It's used in the community now. What you'll see is a lot of people, including ourselves, tend to just use very simple fragments of LTL. But there are some more interesting structures you can build out of co-safe LTL, for example. Okay, I'm going to whiz on a little bit. So the final part that's interesting for talking about here, interesting to talk about, is the mission planning part. So how do we actually take the MDP and produce plans for the robot, policies for the robot? Well, there's an extra step now that I'm going to sort of skip over, but it's important in what comes next. Every task given to the robot is put into a bucket. So the robot will have multiple tasks at once. And that might be to visit a particular location, to map an area, to meet a person, to check some surfaces, run object searches. And these become a large set of tasks that are considered and available for action. And then through some process, which we won't talk about here, we end up with a conjunction of specifications. So one of the benefits of having LTL is that, as well as having individual specifications that are rich, because it's a logical language, we can just create a larger conjunction, which is still a valid LTL statement. So we have a goal for our robot, which is a collection of sub-specifications, as you will. And then we can start to do things like assign priorities and stuff to that, but we won't talk about that too much. What we realized fairly soon on into our process is that if you carry on, if you take this approach, you end up with some interesting dependencies. So imagine I've now got a conjunction of two tasks. One is to inspect the stock room, and the other is to inspect the coffee machine in the kitchen. And if my plan turns out that I want to go to the stock room first, then I go to this, and then I'm going to go to the kitchen afterwards. If I get to the stock room and the door is closed and it doesn't open, then I fail. And in the MDP world, or in our policy world, the probability of achieving the full conjoined specification drops to 0. So I can't do this action. That means my ability to meet the specification drops to 0. Here, what we're doing is effectively solving a stochastic shortest path problem, and the assumption for the default assumption for a stochastic shortest path problem in SSP is that you can achieve your goal with probability 1. So in this case, if my probability goes from if I can't execute an action, my probability drops to 0. Or if, for example, the prediction of my system says, this edge has a transition probability of 0, the probability, my entire conjunction effectively drops to probability 0, and I can't do anything. So that's a problem, and we needed to come up with a way that dealt with that. So there are different ways of dealing with these are called dead-end states in the probabilistic planning literature. There's various ways of doing it. We'll present one particular way. There are many other ways of doing it. And this is something that leads on to other things that we can discuss later, which is ultimately planning for robots are planning problems for robots are either explicitly or implicitly multi-objective problems. We always care about, minimizing something like time. We want the robot to be efficient, but we ultimately care about also maximizing the probability, maximizing the usefulness, not running out of battery, all these kinds of things. So what we found after a sort of year, I think, of deploying the robots based on what was a kind of a cost minimization approach. And then we encountered these kinds of failures. The robot failed on the first bit of its mission or bit of its kind of task, which would maybe be 20 minutes of behavior. The robot would finish within a first minute and then have to replan everything. So instead, we decided to treat this as a multi-objective problem. And for the long-term deployments we did, we had 3 objectives. The first objective with highest priority was to be robust. So we wanted to first maximize the probability of achieving our specification. And in this case, our specification is a conjunction of multiple kind of sub-specifications. So our number 1 objective is with high priority. Oh, sorry, our number 1 objective is to achieve everything with high probability. Our second objective is then to try and do as much as possible. So if that first objective drops from 1 to 0, because the probability of achieving the task is now, the whole conjunction is now 0, we still want to do as much as possible. And so here we track something called progression, which you can think of as how far you've moved through these automata that I showed you earlier, how far you've moved and how far you've got to get to reach an accepting state. So you can track how much you've done in your goal space using these automata. And so our second objective was to progress as far through the automata as possible. That gave us a notion of progression, of getting as much done as possible. And finally, we didn't want the robot to endlessly loop around trying to achieve some small bit of the automata. So only after we'd been robust and tried to do as much as possible did we then try and be efficient. So we wanted to minimize the time to a successful outcome, to a accepting state. But efficiency was kind of the third point. We wanted to be robust and effective first, and then we were efficient. This is a multi-objective problem. In this work, we solved it using nested value iteration. So this gave us a syntactic or lexicographic preference over these terms, which meant we effectively just used the multi-objective criteria as tie-breaking within a standard value iteration process. So we ran value iteration for maximum probability. Then for everything with the same probability, we ran a kind of nested value iteration for expected progression. And then for any action with the same progression, we would then go down to minimizing costs. So it's a nested value iteration. That gives you a kind of particular outcome. It doesn't give you the whole space of policies, but it's much, much quicker than many other value iteration, many other multi-objective solvers. So we also did this in a way that allowed us to extract probabilistic guarantees. So we could look at probability distributions over the time of completion condition on particular observations. So this leads back to these discussions of success and failure. And we use those within the execution monitoring process of the system. So we knew the expected duration, for example, of a policy, which is achieving multiple goals. And we could then say, if we exceed the expected duration of this policy by 50%, then maybe we should consider terminating that policy. So we can use the guarantees that are yielded by solving these MDPs to manage the robot's behavior at a high level. Okay, I'm gonna pause for questions in one slide. Just to say that I'm not going to give you a whole bunch of results or scalabilities and things. Those are in the paper. The key thing is this kind of approach ran robots for years. In our controlled time-limited experiments, we ran this framework for over a year, handling 23,000 tasks. And robustness came from learning about the behaviors of the environment and effectively choosing actions that avoided the likelihood of failure, but in a very large scale. So this is kind of the key motivating thing that got me into the world we're in right now. Has anybody questions about the general framework or this kind of work before I move into some specific kind of follow-up examples?
Okay, there's no questions in the chat.
Okay, cool.
Oh, and now there is.
Oh, that was very in your face. Unmute. There we go. Sorry, I was just wondering what types of tasks you had in this specific problem. You say 23,000 tasks as well. So did you have new tasks given like daily, or did it find new tasks to do, or did you plan for all of these?
All of these things. And I'm going to talk about them in the next slide. So that's a great question. Well timed. In general, and in general, the tasks were things that didn't involve any physical interaction or any limited spoken interaction. The robot would go and check fire doors were open. It would greet visitors. It would check whether people were eating at their desks. It would count people before and after working hours for health and safety assessments. We did some more involved tasks like leading groups of people, guiding them through offices, building a blog of objects that people have left behind on surfaces. A whole range of quite, in some cases, some tasks were useful for people in the environment. Others were things that we could use to get the robot in there, because we were keen on getting the robots into these spaces. So we had to invent things that were useful for the people that were there. Often we worked with the office manager who cared about either the tidiness or the health and safety of the environments. And we would work on with the robots to kind of report kind of times when fire doors were open or closed, or things were missing when they, like if the first aid kit was missing from the location it should be in. So those things was kind of practical tasks we did. To answer the question about the tasks, let me jump through. I'm going to skip the structural bits of the talk. In fact, I'm going to just skip a whole bit of it, and we'll come back to that if there's time, which there isn't. So, in fact, we can think about our task model. So, a task for us was a thing we wanted the robot to do. It was effectively an action that had to be performed at a location. Each individual task had a reward associated with it. It had a duration, which the action took, which we learned. And there was a start and an end time, which had to bound the action of the duration of the action. The start and end time could be the start and the end of the day, or it could be a particular time window within the day. To answer the previous question, we actually got our tasks. So I guess there are two things here. There are kind of instances of tasks and types of tasks. So the answer to the previous question, I described the types of tasks. The question then is, where do those instances come from? And they came from three sources. One was what we called a routine. So the routine was a declarative specification of what task the robot should do when on what day. So that was kind of like a to-do list. Every day the robot had a slightly different to-do list. That to-do list was specified in a mixture of Python that we would write, that we would say, these are the things the robot has to do, and a Google Calendar. So our users could enter events in the Google Calendar that would get turned into tasks for the robot at a particular time of day. We also had tasks that were requested kind of on the fly. We had a web interface where users could go and request particular things. So in some cases, we had the robot with a basket. The robot could then carry things between two locations. So you would go onto a web interface, you would request the robot, and the robot would come to you. And then we had learning tasks, which were generated by the internals of the robot. So earlier I mentioned this ability to explore a particular edge to gather data. So that was where we used some LTL. Those tasks were generated by a number of components within the system on a kind of a curiosity-driven way. So there are these three different sources of tasks. And the interesting thing from an autonomy perspective is the robot had no prior knowledge of what the humans were going to request or what the learning systems were going to request. So it could inspect the routine because that was written out in either in Python or in the Google Calendar, but it didn't know what was coming for the rest of them. And that meant we had problems managing the workload on the robot with respect to the battery. So we had a kind of a new problem that emerged from this, and something we dealt with the data from the deployments later, which was, how can we make sure the robot is available to perform tasks when there are tasks to perform, and then when it's charging when there are low priority tasks or no tasks? So our deployments, the robot ran for 12 hours and charged for 12 hours, basically in that order. It would run during the day and it would stop at night. But when the battery started degrading, the robot would also have to charge during the day to make sure it could be active later on in the evenings when there were still tasks around. So this problem arises anytime when you've got more work to do than you have battery to do that. So we had a large data set of tasks that we'd seen the robot requested for the robot in the past, and we had a data set of battery performance from the robot. And so we used this in some very sort of straightforward, again, I say learning, it's really statistical estimation. We were able to produce a battery model that had a discretized level of battery. So we could say, high, medium, or low. and a probability distribution for transitions between those levels. And we could do the same with the reward that was available at a particular point in time. So we can model and predict in, say, 5, 10, 20-minute time intervals, how much reward is available to the robot, which is a proxy for what tasks are available to execute right then. So we can take the data that we've experienced in the past and use that to predict these tasks that are in the pink boxes in order to manage the autonomy of the robot. So this again leads us to a multi-objective problem. So I saw notifications pop up. I think what I'm going to do is I'm just going to cover this bit of the talk, and then I'll end and take more questions, because I think that's probably going to be the easiest way to do it. So what we had to solve again was a multi-objective planning problem. We wanted to maximize the reward that the robot could get by performing tasks, but we wanted to maximize that subject to a constraint that the robot was not under a dangerous battery threshold. So there are two different battery thresholds you can think of. You can think of a kind of a useful battery threshold where the robot can act for a certain amount of time without charging. And you can think of a dangerous battery threshold. So the battery threshold of at a certain level with the lead acid batteries we were using, they would damage the battery, and we were told by our manufacturer to keep it above a certain level. So we get these thresholds from fairly direct locations. And so we built these models from the data. And this is another example of doing MDP construction online. So we've got some learnt models, in this case, battery and reward models, and we've got some structure, which is effectively the assumptions about how the world evolves and the assumptions about these tasks. So a state in our MDP looks like this. There's a bunch of factors. One is the battery level. The next is the reward available at this in the next, I don't remember what the time discretization is. Let's say it's 20 minutes. So that's the reward available in the next 20 minutes. Whether the robot is charging or not, and what the current decision-making epoch is. So this is a time, but it's more of a discrete time-based indicator that tells us about a larger window of real time. And from the predictive models we built, we can model the stochastic effects of two different actions. On the left, we have the action of gathering reward. So this is the robot to continue acting in the world. And on the right, we have stay in charge. So SC is modeling the stochastic effects of staying on the charging station. So here we've turned the battery problem into a decision-making problem of when you should leave your charging station. And that's kind of a nice way of thinking about some of these higher level robot problems. So when you leave the charging station, we're going to assume the robot follows a policy that maximizes reward gathering, similar to what we saw in the previous sort of set of the talk. But we're not going to model that planning process here. We're going to abstract that into an action that says, robot, go and do some things. And at this higher level, we're going to model effectively just the aggregate outcomes of those actions. So in this case, we have a reward associated to only this action. So gather reward inherits, the reward for this action inherits the reward available at the previous state, whereas the reward available for staying to charge is 0 because there is no task to be done. And then with our transition model that we've learned from data, we can say, well, the probability of the battery moving to a particular level gives us this, and the probability, well, it's probably easier if I show you a few actions. We can then produce a distribution over future battery levels and a distribution over future reward levels. So this says, what do I expect my battery level to be after acting, and what available rewards do I expect to be in the next time state? The next time interval in the real world. And I can do the same for charging. So here the reward distributions are the same, okay, because at that next 20-minute time window, the rewards available will be predicted to be the same, but my battery level will have increased by some probabilistic amount because I'm charging. I can run all those forward, and you can create a time windowed or finite horizon MDP that models for the next n decision points the ability to maximize this reward or avoid falling under a particular battery level. And then what we'll do is we're going to build a policy from this and execute it in a receding horizon way. So we plan for n time steps, but execute one action and then replan. And we do that because we're rebuilding the model frequently. Just one last bit. The solution here is multi-objective. So we wanted to maximize and minimize two different competing objectives. We want to maximize the expected cumulative task reward. So we want the robot to do as many tasks as possible, but we want to minimize the time where the battery is under some particular threshold. In this case, we chose the higher of the two thresholds I talked about earlier. So 45% is a kind of good, useful amount. If you're under 45%, you're going to probably end up getting close to the dangerous sort of 20s after you've done a few tasks. So we want to maximize cumulative reward. We want to minimize the time we spend under a threshold, but these are competing. To get the highest amount of reward, I have to spend more time using my battery up. So you can't optimize these independently. It's a multi-objective problem. And so here we're actually going to generate the full Pareto set of policies, or policies that are not Pareto dominated by other policies. This is something, again, we probably don't have a huge amount of time for. If you've not seen this representation before, the easiest way to think about it is each of these blue dots is a policy that has a particular trade-off between the two objectives. And as you move along that Pareto front, you're trading off which objectives you care about. So on the far right, receding horizon control 4, what we're trying to do here is maximize the amount of reward we get. Okay, so we're maximizing on the y-axis, which is how much reward we get, but we're also then increasing the amount of cost we spend, or the amount of time we spend under our battery threshold. So here we're measuring the time under the threshold as a cost. On the other hand, at the far hit down here, if we spend 0 time under our battery threshold, then we get a lot less reward. And what you can see is this nice curve that as we move through the Pareto front, we can gather more reward, but at the cost of increasing the time we might spend under the threshold. So what we can do is we can pick different policies from this Pareto front. And I think it's an open question. It's a really interesting open question, how you choose which policy you take. There are some kind of rules of thumb, but I think there's some interesting things you can do and treat that as a planning problem in a long-term setting. But please don't steal that idea. I've got a student working on it. This is quite exciting. But we'll come back to that later. What you can see is effectively you can plot the performance. So this is now over, I think, 2 weeks of performance or simulated performance. You can measure the average reward that the robot takes. And that's what these blue boxes see. So on the left, the 4 RHC controllers give you the average reward of each of those controllers around the Pareto front. So the one on the right is the one that's aggressive, that's getting reward at the expense of being under the threshold. The one on the left is a couple up the curve that's a lot more conservative in terms of battery life. And what you can see is actually here you're taking on average, about 77% of the available reward. Whereas if you're very aggressive, you can get up to, say, 85% of the available reward. But the cost is available on this red line. So this red line shows you the time under your battery threshold. And if you go up to this aggressive policy, you're now, just to get that extra 10% of reward, you're now spending almost 40% of your time under that dangerous threshold. So by using this representation, you can plan when the robot should charge and when it should act. It doesn't really interact with the planning system in terms of how you're performing individual tasks. So there is, I think there will be some conflicts there, but it allows you to start modeling from long-term data, the longer term autonomous choices a robot might make. So when to charge and when to act. In this paper, we compared it against the rule-based controller, so RBC, that we actually implemented on the robot in practice. So we gathered this data and did this work after the deployments. And we compared it against the kind of things we were using on the robot, which was really just a fixed threshold controller. And we showed that actually, if we'd used this learning approach, we'd have had a robot that could perform many more tasks than was actually done in practice. Okay, so I am going to stop talking there. And I am going to jump to a quick few slides on where next. And I think in general, there's lots of things we can talk about. The thing that I'm most excited about, or one of the things I'm most excited about at the moment, is this idea of interval, uncertain, or Bayes adaptive MDPs. So everything you do with machine learning, or if you do it correctly in a Bayesian way, you end up with some effectively confidence interval over the probabilities. When we build our MDPs, we're using the expectation of those probabilities, and we're throwing away the confidence of the estimator. You can use things like uncertain MDPs to put that confidence into your model, and then you're not only reasoning about the probability of your outcomes being correct, you're reasoning about the probability of your model being correct. And that allows you to start thinking about robust behaviors or risk-aware behaviors in terms of what you've learned. And I think that's a super exciting avenue to pursue in terms of probabilistic planning for robots. The others are a big list of things that are also interesting, but we won't dwell on those. Takeaways, I think I encourage you, I know you've had some talks on probabilistic planning. I think for me, MDPs, probabilistic planning, is a really exciting way of merging the model-based bits of the world we know and love with the machine learning bits of the world that allow our robots to be robust and adaptable. In particular, we end up often building processes that rebuild our models online. So you have a fixed set of scaffolding, of structure, and you use that to rebuild MDPs, planning models, planning domains for the execution time and the particular task that you are facing. That allows you to adapt to problem and environment specific changes. The other thing we've seen twice here is that long-term autonomy in robotics often require multi-objective solvers. So we need to consider multiple objectives in our planning processes, because those objectives are really there in reality for a physical system in real application domains. So a final thanks to the team. There's loads more people that have contributed, particularly the people in the Strands project that are not formally acknowledged here, but thank you to everyone that supported this work and funded it, and a big thanks to all the students and postdocs that have helped do all the work. And now, time for questions, I think.
Many thanks, Nick. So do you have additional questions on the chat? I have one.
Okay.
Very, very interesting overview. But in this approach where you have a fixed structure for your models that you parameterize with data learned, your MDP state is basically a node in the map which is augmented with additional features that are relevant to the task.
Yep.
Now, my question is, this approach, is it scalable to quite complex tasks? Because from what you showed, you experiment mostly with navigation robots that do not have arms, that cannot change the environment. If you are in a different kind of setting where you are manipulating in the environment, changing the environment and so on, with that approach where a node state is basically a node in space, and here you will have to deal with multidimensional space, will that be workable, and will that carry on in this more complex setting?
I think it's a good question. It's a good question. What we observe is that if you solve these, so I think the two examples I've given you are not great examples in terms of the solvers we use. Most of the ongoing work now is using kind of heuristic search solvers, or either heuristic search solvers or kind of random tree search algorithms. What we see there is that we can quickly rule out states that are not reachable. So if you can build problems where only a subset of your, like complex problems where only a subset are reachable, and you can provide useful heuristics for finding that reachable subset, then we can scale to big problems. If there are state factors that are involved in everything, so if you've got a highly constrained manipulation, like bimanual manipulation task, where every action affects the state of everything else, then I think the state space and the branching factors grow so quickly that we wouldn't be able to scale to those kind of problems. So I think you're right. We are implicitly assuming a degree of independence between some of the actions, or a small branching factor in our actions. So a nice example actually of where these kind of things go wrong is we had a version of the problem where we modeled the state of doors in our state space. And so every state included whether we'd observed a door, whether it was open or closed. And there, the kind of curse of dimensionality hit us directly, because every action had to then think about which doors were open and things like that. So unless you can factor your state space and exploit that factorization usefully, you can run into problems. I think we would run into problems.
Maybe another question, which is more focused on technical. You are using MDPs, and there is a variant of MDPs, which are the stochastic shortest path problems, where you could combine some of the multiple objectives, reaching particular states, going through some particular states, while minimizing some risk, while maximizing some utility functions and so on. Have you looked into that? Have you compared to?
Yeah, absolutely. In fact, most of the problems we solve are stochastic shortest path. Okay. So I didn't really dwell on that, but when you put LTL into it, we're solving an SSP over this augmented state space.
Okay.
In terms of managing objectives over those SSPs, we've got a few bits of work on that, and I think what's interesting is so the answer is yes. SSPs is for us is typically the way to think about it. Most of our long-term behavior is an SSP at some level. And then we may have a higher level system that is doing maybe more kind of finite horizon or receding horizon. We've had some interesting problems trying to convert some of the other kind of risk metrics, like kind of, there's a lot of work that uses interesting risk metrics that just use expected reward and converting those. So it's things like regret-based models. We've struggled to convert them neatly into things like SSPs, but we're working on it. So I think the answer is yes, SSPs. We've looked at some of those risk models, and we're working on it right now.
Okay, thank you. Additional questions? So I see a lot of very pleased remarks and cheers from several people in the attendance.
Cool.
And is there time for another question?
Please do.
I've got loads of time, so I'm happy to keep taking questions. One of the reasons I stopped early was to make sure there's space. So I yield to whoever's in charge in terms of timing. So.
Okay, great.
We have time for one more.
Okay, so just following from the Malik's question regarding the complexity, if you extend this to higher dimensional problems where you have group grouping and moving things, I've heard of things like hierarchical Markov decision processes, but I don't know if they apply to this context or if it's something you've explored in your work. Thank you.
Yeah, absolutely. So we have used them in specific contexts, so they absolutely apply. I mean, hierarchy or hierarchical solutions is something that they're exploited all over the planning community, and I think it's absolutely relevant here. We've been using in some work that's under review at the moment, we're using options. So options are one way of kind of grouping MDP actions into effectively macro actions, where you can, what you think about is an action in one level of an action at one level of your MDP is a policy execution at a lower level. And that allows you, that's one way of increasing the scalability. And there are nice ways of computing the transition functions and things of those options. So absolutely, hierarchies are the way to go for larger problems. Yeah, so I think we're looking at it. The kind of work I showed here, we didn't exploit that because there was no real obvious hierarchies to exploit, I think. And we could scale well enough for the kind of problems that we were facing. For larger problems, particularly, so one of the things we've been looking at is inspection problems where you want your state to include things like whether you successfully observed a particular item, so kind of object search style problems. There, the complexity of the full state space grows very quickly, and you do end up having to think hierarchically about kind of, so imagine you're doing object search over an entire building, you might turn each individual search within a room into an MDP that then becomes an option or an action in a higher level MDP. So yeah, absolutely, I think these things have to be done for scalability.